How do you prove that your code is better than someone else's? Not just that it feels faster on your machine, but that it's, demonstrably, mathematically more efficient. Well, today, we're going to unlock that exact skill by diving into the language of algorithmic analysis, asymptotic notation.
So, let's say you've written a piece of code, and your friend wrote a different version that does the exact same thing. The big question is, which one is actually better? How can we prove, objectively, which one is faster? It's a question every single developer runs into.
Now, the first instinct for a lot of us is to just, pull out a stopwatch, whichever one finishes first wins, right? Well, it's really not that simple. In fact, that method is fundamentally flawed. I mean, think about all the variables you just can't control. Your friend might have a brand new top-of-the-line machine, while you're working on a 5-year-old laptop. Maybe they're using a super fast language like C++ while you're using Python. Heck, even if you run the same code twice on your own machine, some random background process could kick in and totally skew the results. It's just too unreliable. We need a way to talk about efficiency that doesn't care about the hardware or the language. We need a universal standard.
So to find that universal standard, we have to completely change the question we're asking. We have to stop asking, how many seconds does it take, and start asking, how does its performance grow as the job gets bigger?
This right here, this is the core idea. We're not interested in the 5 milliseconds it takes to run today. We're interested in how its running time scales as the input grows and grows. That word asymptotic just means we're studying its behavior as the input size gets ridiculously big, like approaches infinity. Does performance slow down just a little bit, or does it completely fall off a cliff? That's what we want to know.
It's kind of like a race between a hare and a tortoise. You know the story. If the race is only 10 feet long, the hare wins instantly, sure. But the tortoise isn't that far behind. The difference is pretty much negligible. And in coding, sorting a tiny list of, say, 10 items, that's the 10-foot race. Every algorithm is going to look lightning fast.
But what happens when we're not sorting 10 items, but 10 million or a billion? As the input size, which we'll call n, gets astronomically large, that's when the true nature of an algorithm really starts to show.
And this is the key takeaway, right? Analyzing small inputs is easy. But professionals, they analyze for the massive inputs. They predict how their code is going to behave when it's truly put to the test, because that's where performance battles are won and lost.
So how do we actually describe this rate of growth? Well, we use a special kind of mathematical language, and its most famous term is Big O notation. To put it simply, Big O gives us an upper bound. It answers the question, as the input gets huge, what is the absolute worst-case growth rate for this algorithm's running time? It's basically a guarantee that the performance won't get any worse than this specific curve. Okay, let's look at the formal definition. And don't worry, it looks a little scary, but the idea is actually pretty simple. Think of f of n as the bumpy, unpredictable line of your algorithm's actual runtime. We say it's big O of some cleaner, simpler curve, g of n, if we can find a point on the graph where our bumpy line always stays underneath a slightly scaled-up version of that clean curve. It's just a mathematical way of saying, from this point on, I guarantee my performance will never be worse than this.
And this graph shows the concept perfectly. Imagine two lines. One is that jagged, real-world performance of our code. The other is a smooth, predictable curve that represents our upper bound. See, in the beginning, for small inputs, they might cross over. But the definition of Big O means that eventually we hit a point, that's our n0, and after that, our jagged performance line will always stay below the smooth upper bound curve. It's basically trapped underneath it forever.
Let's make this totally concrete. Have you ever written a for loop inside another for loop where both of them iterate up to some number n? Well, for each element in that outer loop, you process n elements in the inner loop. That's n times n, which gives you a growth rate of n squared. We'd say that algorithm is O of n squared. But Big O, the worst case, is only part of the story. To get the full picture, we really need to meet its two important relatives, big omega and big theta. So if big O is the ceiling, the worst-case upper bound, then big omega, written with the Greek letter omega, is the floor. It gives us the asymptotic lower bound. It's a guarantee that for large inputs, the algorithm will take at least this much time. It describes the best-case growth scenario.
And if we were to graph these, you'd see the difference so clearly. With Big O, our performance line is trapped underneath that ceiling curve, but with Big Omega, our performance line is propped up from below by the floor curve.
It's a guarantee that our algorithm won't be any better than this.
So we have a ceiling and we have a floor. But what happens when the ceiling and the floor are basically the same? That's when we get big theta. It means an algorithm's growth is squeezed from both above and below. It's not just a worst case or a best case anymore. It's a really precise description. It's like the hallway that the performance runs down.
The best way to picture big theta is as a sandwich. The actual performance is the filling, and it's squeezed between two slices of bread, the upper and lower bounds. Its growth rate is totally locked in. When you can define something with theta, you have a very precise and a very powerful understanding of how it's going to perform.
So why does all of this matter? Because understanding this language, this is what takes you from just writing code that works to engineering solutions that can actually scale. This table right here, this is your new cheat sheet. On the excellent end, you've got O1, or constant time. This means it takes the same amount of time whether you have 10 items or 10 billion. Like looking up a value in a hash map. It's amazing. On the terrible end, though, you have O of 2n, or exponential time. An algorithm like this might take seconds for 20 items, but could literally take centuries for 60 items. It becomes impossible fast.
This says it all, doesn't it? Knowing this stuff isn't just academic trivia. It's a practical, real-world skill that absolutely defines a professional developer. It allows you to make smart, informed decisions about the code you write and the tools you choose.
So, let's bring it all home. What's the big takeaway here? Stop timing your code with a stopwatch. Start analyzing its growth curve. Use Big O as your go-to for understanding the worst-case scenario. This isn't just theory. This is the universal language that professionals use to build software that doesn't just crumble when the data gets massive.
So the next time you write a function, don't just ask yourself, does it work? Ask, how will it scale? Analyze its loops, analyze its logic, and try to give it a big O classification. It's a shift in mindset that will fundamentally change the way you write code forever.